So, I'm going to go over it on the board as well. It's important to realize that only the system, the bag, sand, takes a reversible path. It's not required that this path is reversible for the entire universe, because you can't do that. In fact, this is not actually possible. Why are we interested in the reversible path from the initial to the final state? You want to determine whether the process is reversible or not. For this, we need to determine the entropy. Entropy can be calculated from the exchange of heat, but only along a reversible path. Yeah. So, put that as a reminder for myself. So, if you lower the bag and extract the maximum possible amount of work in the process and store it all in all the energy gain in the form of E store. Can you see green? Two seconds. E store equals negative work equals the negative change in energy potential. You need to note the thermodynamic state of the system does not change in this process, right? So if you transfer the energy reversibly back to the sun in the form of heat, so Q equals E store. So if you transfer all the energy, so remember, if something falls from a height and it hits the ground, all the energy is converted to heat. But we know that it's impossible to convert all of that into heat and store it. But in this case, we assume that it's possible. It's basically the principles of a perpetual machine. Again, another thing that is impossible. But there are a lot of patents that claim this thing is quite possible. So if you store the heat and raise in the system, i.e. the sandbag temperature to the same value it would have after an irreversible process, this transfers the sandbag to the same thermodynamic state it would after the irreversible process, right? So as it must, the heating causes the same change in internal energy the system underwent in an irreversible process. So in this case, delta U equals Q. So you convert everything to heat, which equals to your internal energy. So the first step is step 1. Delta U plus delta E potential plus delta E kinetic equals Q plus W. We deliberately make sure that there is no heat exchange, and while the bag is lowered into the container, it is in thermal equilibrium because it's insulated with the environment, and there is no process that would cause heat exchange. Q equals 0. The heat exchange dQ equals 0. So the initial and the final velocity of the bag are identical, and hence dE kinetic equals 0. And we know that the thermodynamic state of the bag doesn't change, so the dU initially equals 0. And no volume work. Volume work. Well, volume work. Volume work equals 0. And this is why I don't handwrite things. And volume and the work equals E potential. E potential. So using the general work form, it's important that you can extract this work. And the key is that no heat exchanged. There is no heat exchange in the process, right? There is no heat exchange with the atmosphere. The potential energy is used to do work, drive the generator which produces electricity that is stored in a battery. All these processes are reversible. So if you use the bag fouling to drive an engine to produce electricity. Now, step 2 is the heater. The only effect that heater has is to transfer stored energy into heat. Yeah. So Q equals negative W. And this is clearly an irreversible process. In fact, the heater is a reverse Kelvin Planck machine. Since the heater is not part of the system, this is not inconsistent with the requirements of finding a reversible path for the system. And we see that the irreversibility of the original path has been moved out of the system. So we have moved that irreversibility out. That basically means step 2 system. Can you see that, by the way? The delta U plus delta E potential plus delta E kinetic equals Q plus W, and this is a reversible heating process. Hence, the first law reduces to delta U equals Q. Now, so equation for an entropy. The heat exchanged in the second process only, and this is done reversibly, because falling. There we can calculate the entropy change. Therefore, delta S equals S of final minus S of initial, and ds equals dq over t for a reversible system. And we know that dq equals mcv delta t. Sorry, t. And delta S equals mcv times log of T2 over T1. And for most of the solids, Cv equals Cp, almost equals to Cp, because constant pressure. And the same also applies to liquids, but derivation from this rule is generally longer. But we assume for liquids Cv equals Cp as well. And finding out the temperatures, we estimate T1 equals 293 because atmospheric, and T2 we can calculate from delta U. We know that the infinitesimal change in U equals the infinitesimal change in T for a constant volume system equals Cv. You've all seen this. So the change in U equals mCv delta T equals mCv T2 minus T1. Therefore, T2 equals T1 plus delta U mCv. And we know Cp for sand equals 830 joules per kilogram per Kelvin. Therefore, T2 equals 293 Kelvin plus 9.81 kilojoules, because you've calculated that already, 20 kilograms times 0.83 kilojoules per kilogram per Kelvin equals 293.59 Kelvin. Entropy change. Actually, let me do that here. Entropy change. Delta S equals mCV log of T2 T1. Delta S equals 20 kilogram times 830 joules per kilogram per Kelvin times log of 293.59 over 293 equals 33.4 joules per Kelvin.